Alrighty, let us move on now, continuing with our ray optics, but now we're going to talk about lenses. So, obviously, mirrors, we did this before. Mirrors can change the paths of these light rays, focus the image to particular parts, and in general, the type of things we want to know is where will an image be focused? Is it a real image? Is it virtual? Is it upright or inverted? Things like this. We're going to do exactly the same thing for lenses. Now, the first thing we need to know is the types of lenses we're going to work with are what's called thin lenses. So that means things, where the thickness of the lens is fairly small relative to the size. And the reason we make this distinction is because things like, the lens of your reading glasses are fairly thin, but something like a crystal ball acts as a lens. But a crystal ball is a very, very thick piece of glass. And the thickness of this piece of glass, the thickness of this, quote, lens, is relatively the same size as the whole thing itself. And so the way the rays of light work in a very thick lens is slightly different than a thin lens. Thin lenses are easier to work with, and in general, those are the types of lenses we have in our everyday experience. So that's what we're going to deal with, thin lenses specifically. Now, first of all, the good news is the equation, the imaging equation that we're going to use for lenses is the same as that of mirrors. 1 over f is 1 over do plus 1 over di. And magnification as well. Magnification equation is exactly the same. Magnification is minus di over do. Or if we happen to know the sizes, then it's hi over ho. So these are the same. That's good news. There are some subtle changes we have to worry about. First thing we're going to have to know is there's an equation called Lensmaker's equation. And this is an equation that tells you what the focal length of a particular lens will be. Now, we didn't worry about this for a mirror because mirrors have one side, basically. And so when a mirror is curved, it's curved one way and one way alone. However, when we have lenses, lenses have two different sides, and each side can be curved differently. And I'll show you what I mean. The first basic type of lens we're going to talk about is converging lens. It's also called double convex. And it looks like this. So what you would expect when you think about the shape of a lens, this is what you think about. This kind of curved outward shaped lens. That's a converging lens. It's also called a double convex lens. If you look, there's two sides which are curved. You've got the left side, the front of the lens is curved, and the right side is curved as well. However, they don't have to be curved exactly the same way. For instance, I could curve the front side like this, and then the back side have a very, very big curve like that. So because each side of a lens can be curved differently, the way you calculate the focal length of a lens depends on each one of these sides. And so, if you want to see the other type of lens we're going to deal with, just to see it, diverging, also double concave. Looks kind of like an hourglass shape, I should say. So because, as I said, the focal length depends on each side individually, the equation goes something like this. 1 over f, 1 over the focal length of your particular lens is, first of all, it should depend on what is this lens made of. It's glass, is it plastic, what type of glass is it? So there's a little term in here, n minus 1, where n, if you remember, was index of refraction. And so different materials have a different index of refraction. So obviously the amount of light, the amount of bending that's going to occur in the light because of this lens depends on what the lens is made of. Now, the rest of the equation goes 1 over R1 minus 1 over R2. Now these R's are what's called the radius of curvature. And it's basically how curvy the sides are. So R1 is the curvature of the front face, and R2 is the curvature of the back face. Now, radius of curvature, sometimes it's also called center of curvature. A more curvy face, like this R2 face here, has more curvature to it, will have a smaller radius of curvature. A less curved face, like the front face R1, will have a larger radius of curvature. The other thing you have to be very, very careful about is these R's, R1 and R2, can be positive or they can be negative. Here's the rule. The rule is when you consider light coming in, if the light hits a surface which is convex, then the R is positive. If the light coming in, so take this first lens for instance, this converging double convex lens. The light comes in, hits the first surface, it's convex because it bulges outwards like that. That's a convex surface, so R1 would be positive here. Now then, the light continues and then it hits the next surface. Well, this right side surface it sees is a concave surface because it's caving in. R is negative for concave. Oops. Surfaces. Now, it's very important to not get the naming convention confused here. The converging lens is also called double convex. That does not mean both surfaces are convex. It's just a naming convention. What you have to imagine is as the light comes in, what does it hit? So for a double convex lens, it hits a convex surface first, so R1 is positive. Then it continues through, and then it hits this concave surface, then R2 must be negative. But once you know these conventions, that's your little equation there. That's how, if you need to calculate the focal length of a lens, that's what you would use. These, however, are the main equations. The imaging equation, we saw that with mirrors as well as magnification. Now, what about the ray tracing? Does the graphical method change here for lenses? Well, let's see. Let's take a double convex lens as before. Here is our principal axis. Let's say we know the focal length of this lens is 10 centimeters. So 10 centimeters here. Now for a lens, because there's two curves, surfaces, there's two focal lengths. I'm going to assume this lens has the same focal length on each side. So it's 10 centimeters on the left, and it's also 10 centimeters on the right. So there we go. All right, our object, let's say our object is placed 20 centimeters from the lens, so there's my object. All right, so far set up just like a mirror, only instead of a mirror we have a lens. how do we draw our lines? The first ray, just like before, starts parallel to the principal axis, goes to the lens. Once it's in the lens is going to bend the light. How does it bend the light? It bends the light such that the light goes through the focal point. So, it bends downwards this way. Okay. So obviously, lenses are transparent. It's made of glass. The light goes through the lens. It's not reflecting off the lens. So when the light comes in, hits the lens, it bends down, and it bends down in such a way as to go through the focal point. Okay. What's another ray we can draw? Well, another ray is the one that goes from the object through the focal point to the lens. So, like that. And now, the way the light will bend is it's going to bend up so that it now just goes parallel to the principal axis. So like that. So if you notice, it's very similar to the mirror stuff. The first line is parallel to the mirror, or in this case, parallel to the lens, and then through the focal point. Now for a mirror, it bounced backwards through the focal point. For a lens, it goes forward through the lens, through the focal point. Then the second ray, for a mirror, went from the object through the focal point to the mirror, and then bounced back parallel. Here for a lens, it goes from the object through the focal point to the lens, and keeps going through the lens, but now goes parallel. So very similar. The final ray you can draw is a line that goes from the object to the center of the lens and just keeps on going straight. So that's like the ray that went to the center of the mirror and bounced back at the same angle. For a lens, the line just goes straight through. Now obviously, you can tell by my drawing, I'm not very accurate, because if I was truly accurate, all three lines would converge at the same point, which is right here. I missed a little bit, but that's just because I'm hand drawing. The point is, where these lines cross, that's where my image is formed. So here's my little image. Now, here's a second rule that's changed for lenses than for mirrors. For lenses, since the light does go through the lens, the real side is on the opposite side of the lens, where the light actually goes. The virtual side will now be on the same side as the object. So this image, since the image is formed past the lens, that's where the light actually exists, that's where the image should be, that's the real image. If I had an image formed over here on the left side, that would be considered a virtual image. So it's the opposite as for mirrors. For mirrors, since the light exists on the left side of the mirror, the real side is on the left, the virtual side is on the right. For lenses, it's the opposite. Light can get through the lens, so that's where the image should be. All right, let's consider the other case, a diverging or a double concave lens. Say we have our focal points like this, and we have our object. How do we handle a diverging lens? All right, well, our first line, of course, is the same. Parallel hits the lens. Now, what does it do when it hits the lens? Because this is a diverging lens, the light is not going to bend downwards, it's actually going to bend upwards. But how exactly does it bend upwards? It bends upwards in such a way as if we were to extend the line backwards, it would go through that focal point. Now again, the light doesn't really do this. The light actually goes through the lens. but this is a guide to show us that our line should do this. So that's our first ray. Parallel, hits the lens, and then it bends upwards. And it bends upwards such that if I go backwards with it, it goes through that focal point. The other ray I'm going to draw is going to be the ray that goes straight through the center of the lens without bending. So from here, just goes straight through, keeps on going. Now notice these two lines diverge from each other. They're getting further and further away from each other. They never intersect, so you get no real image. However, if you look backwards, they intercepted back here. So that's my image. If you look at this image, first of all, it's virtual. You can also tell it's upright because the arrow is pointing upwards, and it's minimized. That image arrow is smaller than the original object. Okay. So, the ray tracing for lenses is very, very similar to the mirrors, except now the rays actually go through the lenses as opposed to reflecting. The first ray, the red one, parallel to the principal axis, through the focal point. The other main ray you're probably going to be doing is this yellow one, which is the ray that goes from the object through the center of the lens, where the principal axis is, and just keeps on going perfectly straight. Okay. Sometimes, like for the converging lens, you could do the blue line, which goes through the focal point, but you can't do that with the diverging lens. So remember these two lines, this red one and the yellow one. Those are the ones you're going to be doing all the time. Parallel to the principal axis, through the focal point. Now for a diverging lens, it's the backwards line that goes through the focal point, since they diverge from each other. And then the second line, the yellow one, straight through the center of the lens without bending at all. Now next time, we'll do a couple more examples with the analytical method for lenses, but you can see, once you get the hang of the mirror stuff, lenses stuff comes kind of easy. So, hope this is helpful.